Hi guys, today we have a very special guest. His name is Max, and he and his team are doing something extraordinary. They're basically making us one step closer to break the major barriers we have at the moment in the area of material science. We need to explore new materials. We need to get new properties from those materials. Max and his team are giving us the tool set to boost exploration in those areas of new materials. He brings AI and machine learning into the field, which will speed things up dramatically. And the device they're working on is going to be very affordable. So small labs or enthusiasts or even group of enthusiasts could afford it, which means the level of research might be dramatically boosted on the levels which they've never been available before. I hope you guys enjoy this conversation with Max as much as I did. Here we go. Hey, Max. Nice to see you here on another episode of our podcast. How are you doing, buddy?
I'm doing fine. Hi, Denise. Nice to see you again.
Indeed. It's been a while since we talked last time. I think that was like more than 2 years back in the Danish Technical University when we spoke.
Yes, indeed.
Now I moved to Sweden. So really pleasure to see you here. Really pleasure to have you here. And the reason why is that I would really like you to speak out and share with the world about your fantastic project and what have you discovered and what have you done. But maybe first couple of words about yourself, so you would introduce yourself to the audience and
yeah. Thanks, Dennis, for inviting. First of all, to this podcast. Would be happy to give you insights, of course, limited insights about myself. I originally from Ukraine, came to Denmark like 7 years ago for PhD at Technical University of Denmark, and then stayed for postdoc, both in nanotechnology. And while I was a postdoc, I started this project, Atlant 3 nanosystems. Before that, I studied in US, also in nanotechnology in Chicago, University of Illinois, and in Ukraine. Also, I got studies and degrees in micro nanotechnology. So spent quite a lot of time, almost like 20 years in this domain.
You didn't cover micromanagement, no? That's another area.
No. I'm trying to avoid micromanagement. It's actually spoiling the culture in the team.
That's true. And I didn't know most of those facts, by the way. So really cool. So
yeah.
Now you're doing this this project, and I mean, you have advanced quite far. Where are you now, maybe?
I think we're still early phase startup. So we are a startup 2.5-year-old company. But indeed, we progress a lot. We are a very dynamic team. We actually break in all possible advices that most coaches or advisors give, because they tell that the team should be in one location. We are not. We are in 2 locations, plus we have a lot of freelancers, so part-time, and another contradiction that usually everyone says that you need a lot of money for deep tech to develop. And just to tell you, we do develop a deep tech. It's cutting edge technology, and we started from just idea. When we met last time, you remember, it was just an idea that we discussed, and you have been interested in that. But within this 2.5, a little bit more than that time, we develop from idea to the industrial machine, and even running the commercial projects with companies. So quite interesting. Like, I have always a feeling that we are moving so fast that sometimes I need to understand where we are.
Yeah, that's the thing with startups. But what the tech is about? I mean, you mentioned deep tech. What is this about? I think we haven't touched it yet.
Yeah. So what we do, we develop a special technology for atomic layer 3D printing. So we call it 3D printing, but it's not really 3D printing because we deposit atomically precise layers on a surface and it can create some patterns. We call it 3D printing because it's a buzzword that everyone uses and everyone knows. It reminds of 3D printer, but actually when you start creating layers, atomic layers, until you make a 3D shape, you need like 1,000 or even 2,000 or even sometimes more layers, and until you just get some 3D shape. So here it's more like 2D 3D print, 2D printing. How we made it, we took a few technologies. One of them is atomic layer deposition technology, which is very popular and well established in semiconductor industry. Intel, TSMC, Samsung, all of these big companies, they use ALD for high precision material deposition. The benefit of ALD that you get atomically precise layers, film deposition with a very good adhesion and very good conformality to any type of surfaces. So we took that one. Then we thought, okay, everyone tries to build huge ALD reactors. So why reactor? Because ALD, it's a chemical reaction process. So you can change chemicals one by one and get a highly controlled chemical reaction in a big chamber. So every company on the market, they try to make as big as possible reactor. What we did, we took the opposite way. We built the smallest ALD reactor. So it's a tiny, probably this size, like a small coin, and place it on a motion platform. So we made basically atomic layer 3D printer. This is how we call. Then when we made the first prototype, we realized that it needs so many other advanced solutions, like very advanced software, which is not trivial and not typical to any other 3D printing solutions. We needed expertise how to do the proper chemistry. We needed expertise how to characterize the materials that we obtain. Actually, we needed expertise how to print devices that we want to offer to the clients. So in the end, we end up bringing like 5, 6 different advanced techniques and expertise fields. Now we even considering that the machine that we build, we need to integrate machine learning, more sensors, data, cloud data storage to actually create algorithms for artificial intelligence. And basically with this approach, we want to look into the future.
Oh my God. It's a bit, I'm a bit lucky here. I had my master's in physics of metals and metallurgy. And also I've been working in IT for ever since pretty much. I haven't been having that, but so I understand a bit what you're talking about. But why would you, maybe you could explain, where would you apply the artificial intelligence in the process? Where would you see that?
Yeah, absolutely. I think here I need to give some insight, the historical insight, how the micro devices are made now and why AI and machine learning is quite difficult to apply in existing machines. And why AI, for example, is very popular in additive manufacturing. So in order to make simple sensor for IoT, for Internet of Things, you need to go to the clean room. This is a special particle-free environment lab where you have a silicon wafer and then you have some pattern, some photo mask, and then you go through like 10, 20 machines and then deposit separate layers in each particular machine. For each machine, you also need a separate person to operate. So you cannot actually make a very agile and easy to monitor and control system. I mean, computer systems for all of these 20, 40 machines, because each machine is
a lot of human operations. It's
yes,
basically,
yes. So, and this is the biggest complexity that comes with the current state of the art. or current technologies that in operation. Now imagine when you have a one machine that can do most of the processes that and can replace them. So this is something that we target for. So within our machine, we can deposit different materials, and we also target to remove some materials. And we can process different type of substrates. And when you have one machine, when you have one software package, when you can install different sensors and give corresponding algorithms to the machine, basically it becomes very easy to predict the machine operation and even accelerate processes or even enable new processes. And this is where AI and machine learning comes. And that's the reason, that's the same reason why in 3D printing or in additive manufacturing, AI gains so much attention, because there you also have just one machine that does one particular function, and you can either optimize the processes, accelerate, or even enable new functionalities. And this also brings less human interaction.
I think the last time we also discussed that the machine learning could be used to explore the properties of the materials when you combine different components which are not available for normal combination. That's where you could actually explore the characteristics and use the models which would will help you to actually predict the new properties or find out the components to get to the properties you're searching for.
Indeed, that's the next level that we're looking for, to do integration of analytical and characterization tools, and then have them in a closed loop to the main system. And basically you do the processing of materials, they move to the platform where you can do the measurements, and then with these measurements, either you deposit less material or there's some defects, and then you give feedback to the system again, and you can have a fully iteratable process within just one platform.
And the cool thing about all this, or maybe why this was possible, because the chamber size is so small, so you can actually within the small volume add all those advanced techniques to make all these changes on the specimen you're working with.
Yeah, absolutely.
Yeah, this is super awesome. And I mean, then it comes naturally, like when you have that, what do you have in mind? What kind of future do you see for this machine? I mean, what's the size is going to be like? Because I already saw some photos, like I think you published last week some of them, but I'm not sure if that's the prototype or like already industrial manufacturing. I'm talking about the one with NASA. So what's going to be the size of the machine, and what do you see the applications of that? Maybe we could touch that.
With this technology that we developed, we can go from lab to fab. It's kind of the term used in our field. What it means that right now, for each of the development phase, you need a separate technology and different level of complexity of the machines. Basically, with our technology, we can serve the whole value chain. So we can make a desktop, or we now already made a very compact desktop prototype of the machine that can fit to any research lab. With the same concept, but with a little bit more materials, with more functionality, with more complex control. We can go to prototyping labs where you actually have the concept of the devices or materials tested, and then you can make a full wafer with devices. And then imagine then placing several such modules, we can develop a manufacturing platform. And we actually working in each domain already. So we have interest from companies for R&D, for prototyping, and also for large-scale manufacturing platforms. So that's kind of, you know, I cannot disclose more details, but that's ongoing part. Since you mentioned NASA, so NASA exactly wanted to have R&D very compact tool. So the size of that is a little bit bigger than this cube. So
no,
this cube is about,
kidding me?
This cube is about 10 by 10 centimeters. We made it's 30 by 30, just to give you a feeling of perspective. So it's about this size cube with the whole system. And the idea with this system that together with NASA, it would go to microgravity tests, so parabolic flight. And then when the plane reaches to the top of parabola, there is a microgravity. And then in that few minutes, there would be an experiment on the position of materials, and after that we will characterize them, and of course there would be scientific article, but the goal with this is to develop more advanced system that would work at zero gravity, and do some deposition, some advanced device deposition and processing.
But that means you're using electromagnetic fields, so you don't need gravity here, I guess.
What do you mean by this?
I mean, the way how you deposit the particles is not by the force of gravity, it's the electromagnetic fields, it's some other sorts of interaction that go
not really. So I think I didn't explain how our method works.
It's so many questions I have.
Yeah, absolutely. Why microgravity and zero gravity? Because at these conditions you can grow defect-free materials and then defect-free devices. Why gravity impacts the devices and materials? Because its influence on the crystal formation. So in our case, we don't use electromagnetic impact or influence. We have a printhead, this microchemical reactor made like microfluidic device. So we push through the microchannels, gases, then we focus them to the surface, and then on the surface we have highly controlled chemical reaction. So, and the way how we control the chemical reaction, that we heat the substrate to certain temperature. Like we use 100 degrees, 200 degrees. So there is no laser or any other electromagnetic or direct influence. Of course, infrared is also electromagnetic wave, but it's basically heating the substrate, not the process itself. And with this is how it works. And why we're confident that this would work at microgravity? Because gases do not follow the gravity. So you just push them with the flow, and then where you direct the flow, this is why you get the focusing power and with the most concentration of the gases.
So it's the pressure that you have to work with. Oh, nice. Getting back to the device, you said the size is going to be 30 by 30 centimeters, right?
Yeah. Yes.
So what's going to be the size of the chamber there, and what kind of what's the size of the materials you could produce in this kind of device?
The chamber is almost the same size. So we made our frame, our device, very compact, that actually tightly fit into the box that we provided. And for this experiment, we're going to run a very small samples. I think it's like 5 centimeter in diameter, no, not more. And that's enough for the first experiment.
That's quite a lot, 5 centimeters.
Yeah.
Wow, this is amazing. Do you know when are they gonna do the experiment?
I actually was asked not to disclose, but somewhere end of summer, beginning of fall this year.
quite soon.
Yeah, we have been working on this project since September last year. So we met our NASA colleagues last summer, and then during a few months we settled relations, and then we started the work.
Wow, this is amazing. I mean, things also happen quite fast. You wouldn't expect that to be with such a large organization to happen that fast. But I guess it's because it's really exciting for them and something new.
Yeah, I think it's also the luck to meet the right people.
Yeah, we call it. You can call it luck, but it's a lot of hard work.
Yeah, I would not call it luck, but I did. I call this luck, but from another angle. There was some searching process behind this.
I can imagine. And now it's NASA who is using or who is ordering the prototype. I mean, and you also mentioned the labs. Is this going to be an expensive technology, and who will be able to afford it, actually?
Yeah, for now it is expensive technology. Most of the companies or organizations that can afford is R&D, large organizations or universities or large companies. But comparably to what they spend now on the equipment and processes, it's almost nothing, because they spend tens of millions on, even sometimes hundreds of millions euros or dollars, and here it's way cheaper.
Could you give the range of the prices?
It's about 1% of the current expense level.
So like around $1 million or something? Or?
Yeah. Yes.
Yeah, still quite a lot. But what about the future? How do you see? Will this be more affordable for like enthusiasts, like maybe home labs, or maybe like associations of enthusiasts?
Yeah, we're looking into this space because I think this would be also the future prototyping technology. And of course, we try to see how we can bring affordable solutions, affordable models. The biggest issue for now is the price of the components that we use. And as soon as we will find a cheaper solution, then I think the price reduction would be possible.
Oh, this is pretty cool. And speaking of the availability, but I mean, when you will get such a device, what are the practical applications that you could see? We mentioned a couple of them like already now, but what can you do with it? What can you achieve? Yeah,
actually quite a lot. Of course, not now. Right now, the capacity is limited. Right now, we do development with sensors, integrated sensors with some optical coatings, with some protective coatings, applications for at microgravity, zero gravity. So that's also higher quality coatings at more, not harsh, but some extraordinary conditions. Another application is could be in microspeakers, in printed electronics, in display, in electromagnetic interference devices or protection. So basically many areas. Also, we look into space of quantum device materials and devices themselves. And we look also into biomedical device applications. We're looking into airspace applications, not only zero gravity, but how to use in some other applications. I cannot specify some things for the reason, just giving some of the hints.
What about the maybe I could ask you about a couple of the areas like biomedical. What can this be used there? What parts of the
one of the challenges in this area is that especially in biomedical, let's say if you take cell biology field, is in order to make
cell biology?
Cell biology is a subfield from biomedical field. Sometimes people consider it's even separate. I think it deserves to be separate. When cell biology used for, let's say, T cell immunology.
Oh, cell biology. Oh, sorry, I just misread it. All right.
Yeah. It's also used for stem cells applications. It's also used for, it's called a regenerative medicine. So, or organ on chip. So testing this. So all of these fields, they require high precision monitoring and control microfluidic devices. And sometimes to make these microfluidic devices more important with monitoring with some sensors is quite difficult, because you have a lot of channels, and then printing in the channel or depositing sensors in the channels, it's quite challenging. So our technology is quite suitable for that.
But does that mean that you're going to use some special materials in this field, or are you going to use like the
No, we use quite standard semiconductor materials, or materials from semiconductor applications, because it's not only semiconductor materials. With our technology, we can deposit metals, semiconductor dielectrics, many other materials. And most important, we can combine these materials in one process. It's more how you can deposit these materials. So like you can do the selective deposition, you can do combination of materials, you can deposit them on different surface structures. All of this in combination together can be a very challenging task.
What about you also mentioned optical coatings. In optics, coatings actually make all the difference right now. And I think all those companies that compete in the field for like the best world's products, they use really high quality coatings. And I guess they cost a lot right now. Do you see that this is going to be a cheaper process, or where would you be competitive here?
Yeah, I wouldn't call it's cheaper. It's more enabling. With our technology, we can deposit patterns on curved surfaces, like on lenses, on a very, like in a very interesting way. And more important, you can obtain functionality on these surfaces. What it means that most of the development for this optics for lenses is done with traditional methods, so there's quite complex, and it requires still a lot of machines and a lot of people. Here, basically, with our technology, we can make this processing and patterning inline. So in a very simple way with enhanced applications, and basically this can enable smart optics applications. So smart optics, it's something that how it's the smart glasses, you know, that's a big trend now.
Yeah, and I think they're like they're actually like, some of them are projecting the image on the lens, but you can make the lens being like a screen, or
yes, so that's almost nobody does this, because it's very complex, because you have a curved surface, you know, and the dual processing on this difficult. That's one thing. Second, it's very difficult to obtain high quality. And there are also some problems to get a huge variety of materials, because sometimes you need some fancy materials to be applied here, and this is not easy.
Cool. This is really exciting, because that actually opens the way to this could push the industry forward. Anything else you could see that, you know, could be groundbreaking maybe?
I'm looking into space a lot. I'm looking into quantum material and devices. I'm looking into photonics applications. So all of these three areas.
Tell me a bit about that, because I'm not sure I've heard about photonics application. What is that?
So photonics, it's an emerging field. It's basically making integrated optical circuits on a wafer, when instead of electric signals, you can transmit optical signals. And the reason to use this, because you can get way higher quality and higher speed of transmission of the signal in such optical systems. So this is called photonics. There are also even quantum computers based on or quantum processor based on photonic circuits. So this is a really advanced field. There is a lot of attention in many countries and in Europe as well to this. You can make very advanced sensors on this kind of development, because it's basically a very tiny optical fiber structured in a certain way that you, let's say, if you want to sense a pressure or temperature that impacts on a optical fiber, and you can detect very small quantities. There is a startup next to us that developed a pressure sensor based on optical fiber, and they have a really high sensitivity. You just approach close to the sensor, it immediately detects vibrations.
Wow.
So this is just very simple example. And
so basically, instead of electrons, you're using quantums of light to transmit.
Yeah. And we're looking into this because it's basically, we need to be able to deposit oxides, because that's silicon oxide, a glass. It's aluminum oxide, it's zirconium oxide. So basically transparent ceramic materials or related to this field. It also could be not only oxides, some more other materials, nitrides or other. And if you can selectively deposit these oxides, you don't need to go again through traditional clean room and photolithography processes. You can just do printing of these circuits easily and get all of this working almost instantaneously. So this is the opportunity that would come. But until we reach that moment, we need to improve our resolution, because we have now a limited resolution. We need to develop new materials for this, and this is something that we're working on both tasks. And also develop the expertise in such circuit design, and because that would be a new way to design circuits, so not the way it's done now.
But what would be the advantage? Because now, as I hear it, the scale of the circuit will actually go up. It won't be able to, you will need a certain thickness of the material to conduct the light. So you'll have to, yeah, it's not atoms anymore. It's, I guess, several hundreds of layers that you will need to do that. What would be the advantage of that circuit over the traditional?
The manufacturing.
You've mentioned one, of course, manufacturing.
Yeah, the manufacturing speed. I believe it can be done way faster than it's done now. Second, you can also deposit these circuits not only on silicon wafers or flat surfaces, but also make integrated photonic circuits, integrated on more complex surfaces. And let's say even smart glasses. So this is something that will enable non-electrical signal transmission on optical components. So basically making even displays only with photonics or with some other ways, or even calculating. You know, I'm not expert in this field. That's just kind of free flow of my thoughts. So here, the more deep expertise needs to be involved.
Wow, but that sounds insane already. Sounds really amazing. And it's no one else does that at the moment, right?
No, it's out of current possibilities. So this is something that would come, I hope, with only our technology, and I hope in the next 10 years or so.
When it's going to be much more developed and it's going to be mass produced and
yeah, I think another interesting field, since we started talking about space, with our technology, we are enabling the in-space nano micro fabrication. So we even have a kind of a vision making an in-space nanofactories. So our technology is one of the first that can provide these possibilities. So imagine having orbital micro device or microchip manufacturing station, or even the station or factory that can go to Mars or Moon or elsewhere. So this is something that you can do extremely precisely and like in standalone system.
so this is going to be defect free. It's going to be done on the place, so to say. And is it like to reproduce the electronics that are going to be broken, or is it going to be something that you believe should be produced in space and then shipped to the Earth back?
I think both can be possible. You know, you can at zero gravity, you can make some unique micro devices that you cannot make on Earth. But also, if we want to be interplanetary species, then we need technology that can stay with us on board, and we don't need to go back and forth to Earth just to get some simple sensor. We need to manufacture these sensors, these devices on a fly. So that's exactly what we need.
This calls for Elon Musk, I think, here. Guys who are watching this, if you have connection to Elon Musk, please send him the link to this video. He must know this, otherwise he won't reach Mars and won't be able to reproduce his micro stuff in this ship.
I think he can reach to Mars without us, but
he won't be able to reproduce micro devices.
Yeah,
there.
But in order to make efficient settlement and in order to reduce the cost and actually reduce the risk of living there, such technologies, additive manufacturing or in-house manufacturing technologies are needed, not only like our technology, but many other. So self-reproduceable technologies.
What about, I mean, because as far as I remember, we've been also discussing this a couple of years back. What about the supply materials that you need for your device to work? Could they be also like, you know what I mean? If you have a printer, you need to have ink. What are the thoughts around that?
So our micro nozzle itself, we do 3D printing of this in glass. So that's a special technology. This is something that's not easy, but possible to reproduce. There are other metallic components that we use. They also can be 3D printed. Then it's only the some electronic components that needs to be delivered, but these components usually cheap and not difficult to get. And you know, if we are talking about Mars, they can be produced on Mars quite easy.
What about the gases?
The gases, actually, this is very interesting. We use quite simple gases. And there is a quite hot topic now in the world, people discussing how to use asteroids for in-space manufacturing, kind of asteroid mining, and then reusing all these materials, minerals for in-space manufacturing. So we need gases, and basically any mineral can be turned into the gas. You just there are already a lot of techniques to decompose minerals into the gases, and you can find a lot of gases in space in general. I believe on Mars or Moon there are also some something like gas containing or gas manufacturing capacities or facilities would be made, and so this is something that we can reuse a lot.
What was the third area? What about the third area?
What was the third area?
Yeah.
Space, photonics, quantum.
Yes, quantum devices.
So there are several quantum computing technologies. Again, I'm not expert in this, so please don't judge me. One technology uses photonics for making quantum devices, another ion trapping. And for both technologies, we can potentially use our technology to make the devices and even to make the circuits. Of course, not now, it's in the future, but the materials that needed for this are available. And this is a matter of development in this area. So this, you now imagine, if you can make a quantum processor or quantum device arrays almost at your home or in your lab without very complex infrastructure, this opens a huge opportunities in the future. So basically now everyone has a quite good laptop, which is the size, you know, of A4 piece of paper or smartphone with the same computational power. And then imagine having something with quantum computing power in your home as well. Once the traditional computer was the size of the room, right?
Of a good building, indeed.
So now you can have it in your pocket, so you could see. It's. I think this is a matter of time.
Yeah, indeed. I'm really interested in the material science. That was again part of my studies more than 10 years back. Because I think in many areas now we're limited by that. What about your ideas? How can you push that forward? Do you already have something? I'm really interested in, because you've been having this 3D nano printer, I guess, for at least a couple of months, and I bet you have tried to experiment with it, and I bet you've been playing around. Have you done something cool that you can share?
Yes and no. We have the initial prototype for more than a year. We started printing in January 2020. So since that time, we did quite a lot of experiments. Unfortunately, I cannot talk about this because most of these developments, either we publish as a scientific article or we preparing for patenting. And I can only say that that we do the very interesting work indeed that's related to the field that I mentioned. And with our new machine that we recently announced, this is industrial prototype, we can process 6 materials even simultaneously. We can process on 4-inch wafers. We also preparing a 12-inch wafer holder, so we can do processing on smaller and larger areas. Which applications and what experiments, unfortunately, that's I cannot yet say.
Could I reference some of your scientific articles? Could I put them as
we submit here? Yeah, that took us 1 year to prepare a really good article that we submitted to one of the best journals. I cannot yet disclose this. We're waiting for the results on this. What you can find, you can find our patent application. Now it's a PCT phase. If you just search for atomic layer process printer in Google, and you will find it immediately, because this is the only one type of invention.
Nice. Do you know when the article is going to be live or published approximately?
I don't know. We didn't receive yet the acceptance confirmation. We're waiting. I think if they accept within a few months from now, We now preparing the next publications, also the patent. So for some of the processes and some of the processes that we recently developed, they can be a groundbreaking because they will enable something really unique.
Oh, wow, that sounds really exciting. Well, I'm crossing my fingers for that. And I hope that for me to process this video will take less than a couple of months. So
probably we need to add the additional chapter, like
yeah.
what happened after these 2 months.
Wow, that sounds really nice. About the we all I think loved sci-fi and those guys who have a scientific or engineering background. Most of us, I guess. Of course, I can't speak for everyone, but recently I've been reading Isaac Asimov's book. He there was talking about the like a large sphere that was like a spaceship, which was a large sphere, and there were like there were no conductors in this sphere. The material that which the sphere was built from was basically composed of different materials. So the shell of the spacecraft was having conductors built in. When the material of like a solid body would have non-homogeneous structure, it would have a structure that would enable you to have different physical properties of that material.
So functional zones in the same bulk material.
Indeed, indeed.
Yeah. I think this is very advanced technology, but I think it's possible with additive manufacturing, with combination with many other techniques. Within, I think, 20, 30 years from now might be possible.
If advancing your technology.
I think our technology could be very suitable for this, but what you're talking about is a high volume, large macro objects, and we are a more nano micro object. So we need to consider how we can make our technology suitable for this level of integration. I don't say it's not possible. I just say that's a titanic work that needs to be done.
I understand. And it's very early stages. I mean, 2 years back, it was just an idea, right? This is
yes. We have already some very advanced requests from different companies, and we just tell them, look, we are very fast, but not so fast. You want already to build something really sophisticated. We are a bit just
hold your horses. Let us.
Yeah. We need some time.
Is there a way that you could that those companies which are interested in investing in your technology, could they do that right now? How can they do that? Because I mean, essentially, if you will get good financing, I guess it will speed up your development.
I would say there are a lot of advanced technologies on the market. If when we have access to capital and these technologies, within 2-3 years, we can develop quite advanced solutions, industrial scalable solutions for different areas, because this would be mostly engineering. Engineering and some applied R&D. This is not fundamental R&D that requires years and then you don't know if this would work or not. We are in applied areas, applied engineering, applied physics, applied chemistry, and it's not proof of concept, it's a matter of integration and scalability. So having enough capital and resources, both talents and access to certain technologies, all of this is possible.
But I mean, what I'm asking is like, how can people help you now? How can they do that?
We're looking for strategic investors. We're looking for strategic partners who wants to join this new type of development. We're looking for, very visionary people who can understand, like you, what we do and actually see the big future in this, because that's the technology that's the concept itself that can change many areas. Let's say, if you might remember, we called our machine nanofabricator. So this name comes from a very famous article of that's called nanofabricator, from a famous UK journalist, science fan, and also he is like futurist. And I forgot his name, I need to recall. And he said, nanofabricators, that's the devices that will change the future, because they will enable printing of almost anything. So exactly this inhomogeneous bulk multifunctional materials or bodies that can represent the whole, like a ship or in a car, where you
we're
don't
looking
need
into spacecrafts, right?
Yeah,
because
yeah.
that's where we would like to
So
go.
this is our future. Like, also there are another few very bright scientists like Feynman, and I forgot another one.
Well, Feynman is quite bright.
Yeah, so they also predicted existence of molecular assembly machines. So we are working on one of these molecular assembly machines. There is not so many realized concepts, and those concepts that were realized as molecular assembly machines, they are not scalable. I think our technology, our approach is highly scalable. So that's why I'm very confident to say this is a nanofabricator, highly scalable molecular assembly machine that can go on manufacturing from lab to fab and making a lot of different applications.
Wow! Oh my God! This sounds really fantastic. If we talk about maybe some of the materials which could be, or you think could be easily achievable with the prototype you have, that would have, will be unique. Let's put it like that. Is there a possibility to combine something which is not combinable at the moment? Because again, that's going to be a breakthrough in some sense.
Really good question, but honestly, I don't have yet the answer. And I mean yet, because I cannot predict, honestly. I cannot predict everything and all aspects. Like, there's so many possibilities. We were sitting in the team and thinking, hey, what can we do? And many of these questions we could not answer, because simply it's out of our mental possibilities to predict. Like, what I can say possible from material side, with our technology, we can potentially reproduce even super conductive materials, magnetic materials, polymeric materials, like for encapsulation, the polymers that are used for protection or insulation, conductors, semiconductors, dielectrics. These are the most common functional materials used in many industries. And all of this can be done with our technology. There are already scientific proof for this. How they can be combined, we can just imagine.
No, I don't mean the specific applications of them. I'm just thinking, like, could you combine something which is like, I don't know, dielectrical material with a conductive material that
this is easy.
Yeah, that would be very hard to combine in any other conditions, but with your technology, it will be just like that. Because if you do that, this new material, it will trigger the new studies, it will trigger the new studies of it, it will find its own application areas. Some of them will, some of them will not. But if this is the possibility, that's what I wanted to hear.
It is a possibility. I cannot just predict all possible combination. It's impossible. We can just sit and think, okay, this is the combination: supermagnetic material or superconductive material with dielectric. Yes, it's possible. magnetic materials with dielectric, or it's possible. Semiconductors with some other, it's also possible.
I guess that's why you would like to add to this the material exploration kind of module or part of your project.
Yeah, that's actually one of our earliest products that we want to bring to the market. The R&D explorative tool that you can or one can simply just sit and try different materials, sort of optimizing their properties combined with several ones. So
damn, that's a very cool value chain. But then yeah, that sounds amazing, because that's, I think, could be actually the breakthrough to the material science, and this is a potential to find something which we have not been even able to accomplish beforehand. It was not possible to do so many experiments before. And I mean, if you think about the human history, a lot of the unique materials we have been discovered by an accident, by a mistake. We call it out Nobel. This is from his museum. It was an accident, right? And many other things. And if you have a machine which would enable you to do these kind of experiments at your workbench, so to say, I mean, imagine how far can we get there with it?
I think far away. Like we spent 60 years to reach to the electronic level that we have now, and it was everyone think it was very fast having such technology as this one. And similar, I think we would not need 60 years. Everything would happen way much faster.
Yeah, we have the exponential growth, and maybe this would be the way for us to get out of this plateau.
Yeah. So yeah, if we look on, if we jump into this field like Moore's law and exponential growth for electronics, so everyone wants to reduce the size, but we almost reached the limit. So everyone now is trying to look how to make electronics in 3D, 2.5 3D. And this is also where our technology, our concept can serve really well, I believe. We can potentially create 2D, 2.5, 3D electronics in a volume. That's again coming to what you said, functional zones or functional blocks in monolithic bulk material.
What's, by the way, the current resolution that you could go with? Is it like one atom or several atoms? Or
so there are two resolutions. So one resolution is a vertical, the thickness of one layer. So the thickness of one layer, it's exactly one atomic layer. So depending on material, it can be 0.1 nanometer or plus minus in that area, like 0.1, 0.2. So in order, let's say, to grow like 100 nanometers of material, you need 1,000 layers. And there is a lateral resolution, or lateral or line width, and this resolution is defined by our printing process. So right now it's 400 micrometers. We develop the print head that goes to 25 micrometers now, and our goal to reach to 1 micrometer next year. Then basically this will enable most of the applications that we discussed today.
So it's quite wide layers at the moment.
Yeah, it is, but
I mean 25 micrometers.
Yeah, it is quite wide, but it requires some development from our side, and we are progressing quite fast and quite successfully in this relation. So it's a matter of time when we will reach to the limits that we target for ourselves.
What would be the limit? What do you think?
We next year we're planning to reach 1 micrometer. but
Wow.
we also develop some features that we can go way beyond 1 micrometer. I cannot talk about that.
No, that's, of course, I understand that. All right. Um, Anything else that we should cover about the technology? Anything you'd like to share?
Um, honestly, I can't.
No, that's fine.
Like whatever we can share, it's probably on our website. So please follow our website and LinkedIn page, atlant3d.com. And the same name you can find on LinkedIn, Atlant 3D Nanosystems. Subscribe to the page. We post updates there quite often. And you can see what we can do now, and probably we will disclose some things quite soon.
Just maybe a question from the curiosity. If you would have access to all the scientists in the world for your current team, who would you like to join your project right now? If anyone would be accessible for you.
You asking for the names or for the
yeah? if you have the name, because talents is more wide. But if you have someone specific in mind that you would like to be with you.
Yeah, it's a really good question. I never thought about this. No, I thought whom we need to do certain type of work. Whatever we develop is quite different from what other people do. So it's I would be interested to have visionary people like Elon Musk to on engineering side, because he has unconventional thinking, so which is very appealing to us. So we use untraditional approaches and certain combinations. In terms of scientists, definitely some expert in biomedical devices, in some quantum micro devices, in photonics, some of the best people from this, but also more important even to have people that build quite advanced high precision machines or in space machines. Some talented software engineers, AI experts, this would be quite a lot. And also very good chemists, but actually we have the best chemists in the team already.
Wow. All right. But it's never enough, I guess, when it comes to the
no. One of our co-founders is professor from Germany. He is one of the best chemists in the world in this area.
All right. Sounds good. And if the person like that would watch this podcast, of course, and would really love to join your team, how would he do that?
Just reaching to me on LinkedIn or directly by email. I believe not many scammers will watch this video and especially detect my email. So I can give my email here, mp@atlant3d.com. Just write me email and I would be happy to talk with you. We are always engaged with a lot of interesting people. We're looking for bright, talented people. This is a big nut to crack, and we need you and your ideas to come to us and work together.
I must ask you about the challenges you have now. What are the biggest ones that you're facing right now?
Yeah, we want to move even faster. So our challenge is, of course, access to capital, but I hope we can fix this quite soon. Second, it's again engaging the right people. So, but I think we addressed this already, and and of course, understanding how to structure certain things. But I think it comes with as far as we walk, the knowledge and the right people come. So this is, it's ongoing challenge where we cannot remove it or fix it so far. So it's just one away.
What would you wish your future self from here on, from now, from where we are at this session now? What would you wish to your future self in maybe 3 or 4 years?
Move faster. Hesitation is always good, but some decisions are right. Just go for them.
All right, excellent. Anything else we should cover?
I don't know. I think we covered already a lot.
Covered a lot. Yeah. No, but then it was super awesome to have you here, Max. Really appreciate you spending your time and the sharing to the world the ideas that you have. I really hope that this could also help you. In a sense, it's a pack of information. People who are visionaries, who think forward, who have passion for humanity and for development of the science and technology. Please reach out to Max. This is something new. This is something where you could really change the future world. And it's not very often when you get these opportunities. So reach him out. I'll try to put the link to your page in the description there. And then I'll wish you good luck. And again, Max, thank you so much. And I hope that at some point I'll see your name in the Nobel Museum here in Sweden.
Yeah. Thank you, Denis. Always pleasure to talk with you. And he would be happy to talk with anyone who wants to reach out. And you know, we always open for collaborations and for talents and just smart people, anyone curious to talk to us. And yeah, Denis, thank you for this opportunity to talk. I hope I could cover all your curiosity as well.
Thanks, buddy. It's a pleasure for me as well. All right, then thank you so much.
Yeah, thank you.
Bye.
Bye.